Let's look at a couple of simple things in addition. So satellites, we looked at how to derive various things already. We have looked at many satellite images. One of the more difficult things is to derive winds, especially when they are beyond a certain speed, stronger than a certain speed, because the so-called scatterometers, for example, can look at lighter winds with reasonable precipitation, because the surface wave properties can be related in terms of their reflectances to the wind speeds, and then there are ways to derive directions, or often directions are assigned from models and so on and so forth. For cyclones, obviously deriving winds can be critical to determine its path, its intensity, and its rainfall amounts, and so on and so forth. So here's a quick scatterometry active microwave surface wind speed. So it was shooting microwave and then reflecting and looking at the reflectances, and used wave properties to do that. So you can see that it produces, and since microwaves can go through clouds, obviously it has advantages, but it had the disadvantage that as rainfalls got heavier and winds got stronger, you couldn't do that. But people use rapid scan visible low level winds, so using clouds, for example, and cloud winds can be derived using smart algorithms. Each one comes with certain amount of uncertainty in them, so one has to be careful. Cloud drift winds from infrared, so that's the southern extent of the sector that is an administrative Pacific US sector. 30-minute interval imagery is used here, and 15-minute imagery is used here. So the more the data you have, better the estimate is going to be in terms of converting the cloud drifts into winds. You are assuming clouds are being transported by the background winds in that case. And here WindSat and SSMI passive microwave surface data is combined to derive winds. You cannot see the scales here, but you get the idea that all kinds of satellites can be used to derive winds. They are called deriving winds because they are not directly measuring winds themselves, right? You are interpreting signals from waves and other things as winds, and then the calibration is done with various methodologies to trust the satellite data. There is we have seen that the wind speeds are very high at the lower levels in the eye, and then they drop off as you go outside from the eye and the eye wall. So the measurements of winds inside the eye wall may not be possible, as we saw deriving from satellites or from recon aircrafts and so on can be almost impossible. But if there is a way to derive the tropical cyclone intensity by looking at outer edges where winds are more reasonable to be measured, then it can be useful. So 34 knot or 17 meter per second wind speed radius can be empirically related to tropical cyclone intensity. So if the radius is big, that means you go inside, the speed is going to increase to the eye wall, right? So there is a relation, empirical relation. It doesn't always work, but nonetheless, I think maritime the mariners, people who are out in the ocean with sailboats and other things, often can use these kind of information to derive the cyclone they may be heading to or wanting to avoid, and so on. So TC intensity and 34 knot wind speed radius is used in many cases. In terms of remote sensing of the inner core dynamical features, here are some examples, again combining various satellites, but you see that the eye wall can have a shape that's not as circular as we have been imagining. It has this pentagon shape in many cases, and Here, satellite and airborne radar imagery of Hurricane Isabel, trim precipitation radar image on 12 September, SSMI 85 gigahertz brightness temperature, visible image from GOES Super Radar's rapid scan operation, and radar reflectivity from lower fuselage radar on board NOAA aircraft while flying inside the eye at 2-kilometer altitude. The time of the radar image is 2 minutes after visible image, and so on and so forth. But the multiple data streams can be combined to look at the dynamics, and one of the interesting things that has come out of such studies and then from modeling activities is that the eye wall actually consists of not just this image we saw before of a outward spreading eye with height because of angular momentum conservation, isentropic surfaces. Actually they are equivalent potential temperatures. Nonetheless, it turns out that the eye wall is made up of many vortices of tornado scale, and they are called mesovortices, and it turns out that many of the mesovortices can combine to feed larger scale rotation of the eye wall, and hence are part of the dynamic core or the eye dynamics. Okay, so here is radar reflectivity composite image of Hurricane Rita taken by Eldora on 22nd September 2005 during the Hurricane Rain Band and Intensity Change Experiment RAINX. The flight track is marked by airplane icons, so you can see the tracks being followed by the aircraft. Okay, here is an image that shows multiple mesovortices. So this is the Hurricane Harvey as it approached the coast. So fine scale Dow radar imagery from I think this is Doppler something weather radar from inside the eye wall of Hurricane Harvey, radar reflectivity and Doppler velocities. A ring of convection comprising the eye wall is highly perturbed by 4 mesovortices labeled A to D here. Okay, from inside the eye, wind perturbations caused by the MVs are especially visible. Dow location is the dot here, yellow dot. Black rectangle is zoomed in area shown in figure below, illustrating the tornado scales. Okay, so these are the scales here. So you can see the velocities in meter per second and the size of 5 kilometer radius here. Okay, so obviously the eye wall is very active and made up of mesovortices which are spinning up from the rising motion, and they are not dissipating energy. They can actually be aiding the overall strength and intensification of the eye wall processes and the dynamics. Okay, so that's kind of the brief introduction to these various data streams that have to be used to measure winds, estimate intensity, and look at the eye wall processes. And fortunately, many of the models are apparently able to capture these tornado scale vortices. When we say models, there are very high resolution hurricane models that are used, cyclone models that are used to understand processes, and those are not necessarily the same models that are used for forecasting cyclones. There is attempts, of course, of translating the understanding of the core processes and put them into the typically lower resolution hurricane forecast models. So that's kind of a detail that we are not going to touch on here. Okay, and there are newer satellites and instruments being conceived and designed and tested for better capturing the wind speeds, core dynamics, and so on.